Okay. So yes, we will actually continue. So we have like a different type of sensors, and we will look into to call NTC sensor, NTC transducer design. As I told you, if a sensor have like output voltage, electrical output, we can directly connect to amplifier or signal conditioning. If it is has like what to call sensor, if you have electrical output, you can connect to signal conditioning. Okay, but if the sensor actually have like what to call if the sensor react but not, it doesn't produce electrical output, resistance change, then you have to design as voltage divider or Wheatstone bridge. Why am my handwriting very bad now today? Let me learn to write first. Or Wheatstone bridge. Then only you can connect to signal conditioning. Okay, this is actually signal conditioning. Usually amplifier now. So if it is this is actually usually we call it as a active sensor, and this is actually we call it as a what is that, passive sensor. Okay, but not like all active sensors actually can produce electrical output by itself. Some actually still need to give like power supply. Okay, anyway, so we had looked at that day on designing the sensor for what to call usually what it will given, the operating range actually will be given for the sensor. Okay, usually the operating range actually will be given. Operating range actually will be given. Range will be given. Okay, this should be given. Okay, if it is not given, you have to design by yourself. You choose your operating range according to the application. Like that day we discussed about, if it is human body and temperature monitoring system, choose appropriately. Like for example, to 30 to 45 degrees Celsius, something like that. Okay, and that day we assume that we actually choose like what to call one of the value here. Okay, what is the value? I forgot already. I want to use the same value. We design from 15 to 15. I'm not so sure. 5.
Yes, 5.
5 to
15.
5 to 15. Okay, we design 5 to 15 again. Just to for you to recall this one. So this beta is actually from the data sheet here 4250. If you see here, this is actually the beta. Important information from here. This is actually 4250. This is 15K sensor, which has the what to call the room temperature 25. You see at 15K, sorry, at 25 degrees Celsius, the room temperature is actually 15K. Okay, so these are the important information from the data sheet actually. So with the beta, this value beta 15K and 25 sufficient enough for you to calculate any temperatures resistant. Okay, so this the R2 is actually temperature that you want to find. This is what, sorry. Okay, this is a temperature that you want to find. This is what you want to find. Okay, and this is actually the R25. Okay, which is in this case 15 kilo ohm. Okay, and T1 is this T1 is what to call 25 plus with 273, because we need to convert the temperature into Kelvin, which means this is actually room temperature. And this is the temperature that we want to find. This beta is actually, according to this one, actually 4250. Okay, so everything actually known, we can calculate the resistance for any temperature using this equation. Even though they didn't give the data sheet, it is okay as long as you have this information is still sufficient, right? So the operating range actually 15 to 5. Operating range actually 15 to 5. Sorry, 5 to 15. 5 degrees Celsius to 15 degrees Celsius, right? So for this operating range, we are going to design our transducer. But first, before we design our transducer, we need to get what to call the resistance for 5 degrees Celsius and 15 degrees Celsius using this equation. So R2, I think we do want to use R2 that day, so that we don't want to get confused with this R2 and R from the voltage divider. So let's call it as RNTC. RNTC, sorry, equal to 15K times with exponentially 4250 1 over T2 is the T2 for this one actually 5 plus 273, which is 278, right? And this is 15 plus 273. This is 298, right? Or 288. 15, sure. The day we choose 15. 288 to 298. 288, this one. Sorry. Two seven three plus 15 is 288. If there is any messages, let me know. Okay. So you just going to substitute the for one by one. We'll do for first case for our NTC at 5 degree Celsius. So here T2 will be 278 minus 1. The T1 is actually here. T1 actually 273 plus 225. This is actually 298. So what you got the day? 40 something, right? Is that the same sensor or this is actually different sensor? I don't know whether it's the same sensor, because I lost the something happened with my OneNote, crash the file. Oh, calculate again and then let me know the 41.85
41.85K.
K. Thank you. Kilo ohm. So similarly, you'll calculate for our NTC at 15 degrees Celsius. So this should be 20 something, right? The day we get 15,
24.61 K.
24.61 kilo ohm. Okay, thank you. Okay, we got these two, and then we actually move forward to, because this is actually, you see, for our operating range where we define as 5 to 15 degrees Celsius, we obtain the resistance. At 5, this is actually the resistance. At 15, this is the resistance. But later we want to connect with the amplifier to amplify the signal. So we don't have any voltage here. So we need to translate this on to voltage. Therefore, we will use voltage divider. Okay. So just to recall voltage divider, you will have like a 2 resistance with the power supply, R1, R2, then you will have a V out. This V out will be given as VCC multiply with R2 plus over R1 plus R1 plus R2. So this is actually the expression for the voltage divider. Why we want to use the voltage divider? Because the sensor produces output in terms of the resistance, and I want to translate this information to electrical output. That is the reason I'm using the voltage divider now. Okay, so here where I will put the NTC, I will put at top, so that low temperature will have like a low voltage, high temperature will have like a high voltage output, just for the better understanding. Actually, you can put anywhere because later you can program. But if you want to make it like a low temperature to have like a low output voltage, and then high temperature have like a high output voltage, and you have to put the temperature, I mean the NTC on top, as replace the R1 as the NTC. Okay, give me some time. I want to turn off my speaker. Okay. So come back again. So we now, as for the transducer, so this will actually will become our so this actually will become our RNTC. So NTC, sorry, not RN. Yeah, RNTC also can. VCC. And you could, if the question doesn't give any resistance to you, so you can assume any resistance. I choose like to have like a 10K resistance here. And I'm going to calculate the V out for both cases. Okay, for both cases. For what is that? 5 degrees Celsius and 15 degrees Celsius. Okay, so for 5 degrees Celsius, at V out 5 degrees Celsius will be VCC. Also assume, I assume here like a 5 volt. 5 times with R2 is 10. I don't want to put the K there because all of them actually will be in the kilo ohm. 41.85 plus 10. What is the voltage that you get that day?
0.96.
0.96. Okay, similarly, you will calculate V out for 15 degrees Celsius. What is that?
1.44.
1.44. Okay, some actually ask, I don't know which person the name, I don't know. I should have tried. If you put on the other side, you will get here low high voltage, and here you'll get like a low voltage. If you have tried that one. I think I stopped here in the last class, right?
Yes.
Okay, I stopped here in the last class. So once you have this 2 voltage, actually you can go for the next stages where if you want to amplify this the signal, because you see the signal actually now it's actually vary from 0.96 to 1.44. This is not sufficient to fully utilize the ADC. ADC like Elvis and what is it? Myrayo actually it works on with ADC of 5 volt. Okay, so 5 volt means 0 to 5, almost approximately 0 to 5 could be used, but our device now only giving the voltage from 0.96 from to 1.44, which is very small. Okay, not even 1 volt. Okay, even 1 volt. So this actually will give like a what to call it, won't give like a good sensitivity later when you design this as a whole sensor system. Okay, so um, always remember when you have like this. Now always go with the block diagram. You have a sensor now. This is our transducer stage. It will be good. It will got connected to the amplifier. This is the signal conditioning. Then it will go to the ADC. Okay, if ADC actually operate at 5 volt or voltage reference voltage, so to fully utilize the ADC, my output of the amplifier should range from 0 to 5. Okay, but what is the input to the amplifier now? It's actually from 0.96 to 1.44. So how are we going to change 1.44 to 5 and 0.96 to 0? That actually we will study in the signal conditioning chapter. Okay, we will study in the signal conditioning chapter. Can? Okay, so this is actually one of the, I hope you understand what we are trying to do here, at least on how to use the data sheet and understanding this equation, using the equation correctly without any careless. Don't put k hole here. Don't think this k is actually like 1,000 and then do some mistake. And the units all, don't be careful with the units and everything. The common mistake usually I find, especially those who didn't come today for the class, maybe they do this mistake. What they do, we ask this question, right? 15 degrees Celsius and then 5 degrees Celsius, both they include here. This is T2, they assume as a 15 degrees Celsius. T1, they assume as 5 degrees Celsius. They substitute both T of 5, 15 and 5 here, and then they calculate R. So they won't have 2R there. They will have only one R NTC. They won't use the 25 degrees Celsius. This is actually the common mistake. Usually students who always do in the assessment final exam or test. Okay, so try to avoid the common mistake. We have two temperature for the operating range. So remember that I need to get for the min and max. Okay, this is minimum and maximum operating range of the, this is min, come on, min and max. You will have two temperature, so you'll have like a two voltage there. Okay, min, minimum and maximum. Okay, so this is actually the operating range. And if you want to what to call what is that, connect with your application. So you might have like some at particular temperature range, okay, particular temperature range, above or below at particular temperature range, your device to produce some output. Okay, so this actually our range maybe at 7 degrees Celsius. At 7 degrees Celsius, okay, where to write? Okay, here. At 7 degrees Celsius, what we can name it on this one as 5 to 15. Mm, let's say we call it as a cooler system. Okay, so from 5 to 15 degrees Celsius, the operating range. Let's say at 7 degrees Celsius, above, not at 7 degrees Celsius, above 7 degrees Celsius, let's say. T greater than 7 or 10 lah. 10 degrees Celsius. Turn on the cooler. This is actually like a the output device. We call it as an output transducer. Okay, turn on the cooler. T greater than 10 degrees Celsius, turn on the cooler. Okay, so when you design the whole thing, okay, when you design the whole thing for this particular operating range, min and max, okay, when T greater than 10, this is actually one of the temperature that going to be used in your system, a critical value. So this is known as a critical temperature or critical value for if it is other sensor. Critical value. So you need to calculate V out for this one also. So you have to go back and find what is the RNTC at 10 degrees Celsius, and you substitute RNTC of 10 degrees Celsius here and get the voltage here. Then only you can do something with your programming later. Okay, this is actually quite low level programming. Okay, quite low level programming, but at least you should know the V out. If you want to know the ADC, even if you don't want to know the ADC, at least you should know the V out after the amplifier. Then only we can write the code properly in our lab view, even if you don't want to change to ADC, because ADC done by the our lab view. But you should know what is the V out over here and what is the V out over the after the amplifier to be used in your programming later. Okay, so I hope you understand on that part. So you have to find same process R NTC at 10 degrees Celsius. You have to find this one first, then V out at 10 degrees Celsius. What? Okay, you have to find this flow later. This actually will happen later. V out of amplifier at at 10 degrees Celsius. This actually will happen later after you learn the signal conditioning. This is overall flow of this design. Okay, I don't want to touch the signal conditioning on this week itself. I don't want to burden you. Okay, a lot of information. Any question? Is there any question from your side? Is there any question from your side? Okay,
Awesome.
try to grab as much as possible that we're discussing. Okay, give you like a 5-minute breaks before we continue with the other sensor. Okay. All so far so good. Okay. Or you feel like it's actually very difficult? Honest answer from your side.
It's all right, sir.
No? Can
Can.
Okay. So we will move into a new sensor, one more sensor. We tried to cover the temperature sensor today. And this is, I'd like to go to LM35. The issue is now I lost everything, everything. Let me check. LM35, okay. I couldn't find my search here. Copy image. Okay, you can see right the screen with the LM35 image. Oh my god.
Yes, sir.
Okay. So LM35, it will look like this later in your lab when you can see that LM35 almost like a BGT. You can sense the temperature on top of this part around here. The temperature will be sensed by the LM35 here. Okay. And you will have like a 3-pin. One is actually connected to the supply, another one actually connected to ground, and V out. It will be self-generated by the sensor itself. You don't need to design a voltage divider or Wheatstone bridge to get the voltage. Okay, this is quite straightforward sensor and easier for us to deal with compared to the NTC. Okay, so usually we will connect to 5-volt VCC. Okay, this is actually connected to ground, and you will get the output of 10 millivolt per degree Celsius. Okay, the step size actually 10 millivolt per degree Celsius. You actually can use it from 55 to 155 with certain configuration with the LM35, or 0 to 100 with certain configuration. Okay, you can look at the datasheet later. Let's say we assume that we are going to use the 0 to 100 degree configuration only. Okay, that's actually at circuit level. Okay, if you just change the circuit in a different configuration, it will give from 55 to 150. Another one 0 to 100. If you just straight to connect VCC, ground, and V out, it only will give from 0 to 100, I think. 0 to 100. 0, not even 0. A little bit higher than 0. I'm not so sure. Later you can check. Okay. Anyway, using the same what to call that operating range. Yes, now we have operating range of 5 degrees Celsius to 15 degrees Celsius, correct? So if you use the LM35, this is the V out of the LM35. V out at 5 degrees Celsius, it just 5 times 10 millivolt. Okay, actually you have like a per degree Celsius here, and you have a degree Celsius here. This will be cancelled. But if you just want to write 5 times 10 milli also can. So this is 50 millivolt, and be out at 15 degrees Celsius, we'll have 15 times 10 milli, we'll have like a 150 millivolt. And this is, if you write in decimals, this is 0.15 in volt, and this is 0.05 volt. Okay, so this is also very low output voltage, for the two different temperature, 0.15 to 0.05. Obviously it will need amplifier to improve the what to call that, sensitivity of the device, overall device, to have like a better measurement. Okay, so again, so just draw the block diagram for better understanding. Every time you have your transducer LM35 here, you have your signal conditioning, amplifier, and then you have a ADC. Let's say the ADC reference voltage actually 5, so amplifier you should get output from 0 to 5 to fully utilize the ADC range. And now what is the output from here? Output from here, so is just 0.05 to 0.15. Okay, we need to do something here so that it can get 0 to 5 free, so that it can actually free, therefore the full range of the ADC can be utilized. Okay, LM35 actually quite straightforward. Okay, no trick or anything here. Any question on this part? So whoever actually got LM35 as their, what is this, a sensor for their mini project, you should be grateful, and you should design the circuit actually properly. Like if, for example, if the student actually use like a NTC, they couldn't get the accurate result, or they have some problem, we still tolerate. But once you get LM35 and then you say that I couldn't get the output, we won't tolerate, because it's actually quite straightforward sensor where you need to design the voltage divider. Okay, less hassle with LM35. Yeah, but luck whether you get this one or not. But many students, few groups, I think. LM35 we give like a few groups only, not many groups. But even the few groups, not all actually achieve the correct sensitivity. Okay, manage to get the correct sensitivity of the device. Okay, although their lab view actually okay, but at the device level it is actually very weak. Okay, LM35. Supposedly they should have get better result, if you ask me. Any question on this part, LM35? LM35. Okay, then one more is actually there's PTC. Okay, PTC. PTC actually positive, what we call positive temperature coefficient. Positive temperature coefficient, PTC. This is the PTC. Okay, this is the PTC, where it almost looks the same like a NTC, but the operation is positive. For example, let's say we look at the graph here. You see, it works at this temperature not so good. Okay, but after that you see Tn actually the normal temperature that we can use for this PTC is actually like a 80. So you cannot use less than 80, you know, less than 80 it doesn't act like a PTC. So after 80, and this is actually after 90, this works nicely. This is different PTC, different PTC. Okay, we just observe one of it. Okay, observe one of it, and then we try to using our discussion now. Can I paste directly to OneNote? Okay, can. Okay, PTC don't have any equation. Okay, we only can refer to the datasheet. Even if there is an equation, we will give and you can use it. So as I told you before, and don't bother about the equation given. Equation could be anything. Okay, you just need to have like a information to be used in the equation and get your either output voltage or output resistance. If it's output voltage, okay, straight you can connect to the signal conditioning. If it is not voltage, if it is resistance, you have to design a voltage divider. Okay, we cannot use the same temperature here because this is actually different temperature, quite high. Let's say I'm using this T and the second PTC here. Okay, and my operating range, my god, range is 100 to 125 degrees Celsius. So I'll give this one as a homework for you. Later you do it and check. So you have to find 100 to 150, quite make it quite large. 150 go down. Okay, I got 100 to 150 degrees Celsius. So what is supposed to do at 100, you have to find the resistance. What is the resistance? And then at 150, what is the resistance? You use the second graph, you know, that's actually referred to the N90. So at 150, what is the resistance over here? You have to find. So I'll just give a hint. You have to get the RPTC at 100. Sorry, 100 and RPTC at 150. You should get from the datasheet, no calculation. Okay, so this is actually first step. Second step, design using voltage divider. Okay, VDR, voltage divider. VDR, right? They call it voltage divider. VDR circle lah. Okay. But for this case, you have to put the PTC at bottom if you want to have like a low temperature, low output voltage, and high temperature, high output voltage. You can assume, because if you want to have like all same, so assume VCC 5 volt and you are given 100 kilo ohm resistor, sorry. Okay, 100 kilo ohm resistor. So you will use this 100 kilo ohm resistor in your, what you call that, voltage divider. So this is all actually you have to do by yourself. You can do now, also can do, or later if you want to do also you can do, but this is the flow. Okay, so I believe that's all for today. Okay, that's all for today. We covered 3 temperature sensor. We have one more later, RTD. So next week I'll proceed with the RTD. Okay, proceed with the RTD, and then yeah, then I think should be okay. I just want to ask one thing, discuss with you one thing today, because I believe Friday many of you actually will be missing. Okay, do you have any tests on Tuesday? I mean tomorrow. Do you have any test night? Anyone having any test?
What, sir?
Yes, doctor.
Yes.
Or easy people. Thursday night. Thursday night. Anyone have test? I think can stop recording.